I'm very happy to introduce our next speaker, Sally Benson. She's a professor of energy resource engineering at Stanford, but currently serves as the Deputy Director for Energy at the White House Office of Science and Technology Policy. So Sally, welcome.
Okay, terrific. Anyway, thanks so much. And I got to listen to the last two talks, and I will say they were both really extraordinary, a really incredible group of people you brought to talk with you today. So I'm going to add more because obviously there's a lot that's already been said. And in particular, I'm going to focus on one dimension of this and making the point that it's time to start thinking more about energy systems integration. And as we go through my remarks, hopefully that will become clearer. So if you could go to the next slide, please. Okay, so before I jump into that, though, I'd like to provide some context of the current strategy for the US to get to net zero emissions by 2050. If you're not familiar with this, there is a long-term strategy that was released late last year around the time of COP26. And it laid out not a single strategy, but a number of different scenarios that could each of them get you to net zero by 2050, including meeting the 50 to 52% reduction in greenhouse gases by 2030. So this is the trajectory that you see that we peaked, historical emissions peaked in around 2005. They've been going down slowly, and obviously we need to dramatically accelerate the reduction if we're going to be able to meet our goals. So if you could move on to the next one, that would be great. Okay, so let's look a little bit what's under the hood for those projections. These are all model-based projections. They were done using a combination of NEMS and GCAM. And so clearly a hugely important dimension of this is getting to a net zero electricity system. Because it's so enabling to decarbonization of other sectors through electrification of vehicles, heating, some industrial processes, and so forth. So here what we have is a range of scenarios on the right-hand side. And you can see that clearly that renewables are going to grow dramatically between now and 2050, and even between now and 2030, we're talking about doubling to tripling the amount of renewable generation on the grid. But there are also some other important things you see that as the fossil fuels decrease, we anticipate that nuclear energy will stay flat to potentially increase as some of the new advanced reactor technologies become available. And the other thing we see on this is that carbon capture and storage on natural gas primarily, but also potentially on some coal plants, will also contribute. So the point here is that, which is very consistent with almost every other study that really looks at how do we get to net zero, we're going to need a combination of renewable generation, which may actually provide the bulk of the power to the system, but we need some kind of clean, firm power that's going to provide that reliability and resilience that we need. I've got a last item here, nuclear fusion. For any of you who've been following our work at the Office of Science and Technology Policy, we've gotten quite interested in both the private sector investments and successes in developing fusion technologies, and have been working with the Department of Energy to create a sort of a bold vision for how we might try to pull up the timeline for getting first light from fusion and then quickly converting that to a commercially available technology. So maybe that happens, doubtful that we'll make any contribution between now and 2030, but hopefully shortly after that, we'll begin to see some opportunities. So that's the electricity sector. So let's move on to the next one, please. Okay, so what this does is it looks at a number of different sectors. So we've got the transportation sector, again, dropping rapidly, though a little bit slower than the electricity sector emissions dropping. The industrial sector, which often called hard to decarbonize, is also dropping more slowly. And then buildings, again, are slower. So the two really fast actions we anticipate seeing, particularly in the 2030 timeframe, are vehicle electrification and dramatically reducing the carbon intensity of the grid. Another very important dimension of this is the carbon dioxide removal. Globally, it's anticipated we're going to need many gigaton scale of carbon dioxide removal to mitigate very difficult to abate emissions, or also potentially to manage an overshoot that may occur if we're not globally able to reduce our emissions fast enough. And on the right-hand side, I also, again, sort of highlight the important role that carbon capture and storage would play, not only as a potential way to provide decarbonized, clean, firm power, but also for hydrogen production, for industrial processing, particularly things like steel, cement, ammonia, chemicals, and so forth. So again, I think the key point here is that at this moment in time, we're looking at a very broad and diverse portfolio of technologies that are going to get us all the way to net zero and help us meet our 2030 goals. So moving on to the next one, please. Thank you. Okay, so this is sort of summing things up, and it indicates the major actions. So the first thing is improving energy efficiency. There are significant opportunities with transportation, buildings, industry. Next is decarbonizing the electricity sector. And again, we've already talked about that. That's going to be a blend of different approaches. But again, key will be having some kind of clean, firm power in addition to renewable generation. Next are energy transition. So basically doing things a different way. So hydrogen is expected to play an important role in decarbonizing some end use sectors, for example, heavy duty transportation, and perhaps some industrial applications. Low carbon fuels, looking to the roles of biofuels or synthetic fuels that are actually made from captured carbon dioxide through electrochemical processes. And then finally, electrification of things that are currently done directly with fossil fuels today. We're also going to need to make a big effort to reduce non-CO2 greenhouse gas emissions. And we're going to have to also reduce land emissions. These are very significant. About 20% of US emissions are associated with land use change or agricultural practices. And this is an area where I believe we need a lot of work. And then finally, carbon removal technologies. So again, a portfolio of actions to get us where we want to go. So moving on to the next one, please. Okay, so key actions from the long-range plan: net zero electricity by 2035, improve end-use efficiency in buildings, transportation, and industry, electrify light-duty transport, heating, and some industry, shift to low or no emission hydrogen for hard-to-abate sectors of the economy, use carbon capture where it makes sense economically, and shift to carbon neutral fuels. These could be sustainable biofuels, or also, as I mentioned, electrochemically produced fuels. We also, again, need reduce non-CO2 greenhouse gases, carbon removal, and again, agriculture. So a long list of actions that are going to be needed. So we need everybody engaged in this. We have a lot of work to do. So moving to the next one. Okay, so now I want to shift. So this is lays out a broad vision for an action plan, a nationwide action plan. What I'd like to do is sort of step back and share my perspective on the energy system transition, decarbonization, as it's evolved over the last 20 years or so. So if we look at the energy system, we clearly have our energy resources. In the old days, we would basically say that these were fossil fuels and maybe biofuels for wood, and for example, nuclear has been around for a while, but today the sun and the wind, are clearly new energy resources. And we've put a lot of effort, really beginning in the 1970s, to develop a suite of technologies that allow us to take these resources and convert them into useful energy that can be used for a variety of end-use applications. So all of these natural resources require then energy conversion technology. And this is a huge focus of engineering for, more than a century. Generators, PV, internal combustion engines, steadily getting better, including on things like PV, which continues to improve. Again, a huge amount of investment has been made there. And then I want to skip over that next column in the middle and jump to the end and look at the end use conversion. So cars, buildings, industry, a lot of emphasis on how we efficiently and effectively use energy that's delivered to the point of use. But there's this big middle piece that the transportation system, the pipelines, power grids, rail, trucks, all of this is moving energy around from where it's produced to where it's used. And then a very important component of this, and not terribly visible to us today, is that there's also a large amount of storage in the energy system. For example, we have massive amounts of natural gas storage, which allow us to balance supply and demand over the course of the year. So things like tanks, batteries, reservoirs, and caverns. And I think that this block, this sort of middle part that has been optimized to be able to provide basically, up next, could you click forward 2 of them, please? Yeah. So all this sort of middle, this midstream energy infrastructure allows all 4 of these components to work together, and they do it in real time, and they do it essentially all the time. And it's the sort of invisible part of the energy system that really makes it work. And if you've spent time in developing economies, it's often this middle part of the energy system that is really not yet mature enough. And in reality, that this whole system of transportation and storage is coordinated by a massive cyber physical infrastructure that I believe has gotten less emphasis or less attention than these other components. Now, perhaps that was perfectly appropriate, because if we don't have new ways to generate electricity, we really need to think about transportation and storage and so forth. And if we don't have end uses for these new forms of energy, then it's not really worth thinking about how do you get it there and keep enough of it on hand so that we can always meet supply. But now that we've got inexpensive wind, we've got EVs, we've got inexpensive solar, we have all these things now. And I think we need to spend a little more time thinking about this midstream and making sure that we're making the right investments in infrastructure, but also innovation to address this issue. So if you could go to the next one, please. Okay, so amongst all of this sort of more invisible part of the energy system, the reality is that real-time delivery is going to get much more complex. That the lowest cost sources of energy are going to come from variable sources like the sun and the wind that we don't control. Also, many of these new kinds of generation are inverter-based. And the current electricity system today relies on the inertia of spinning generators for stability. We're going to need to find a new way to create that in a synthetic inertia that stabilizes the grid. And the second point is that electricity is likely to become our primary source of energy for 50% or more of end uses. So today, about 20% of our end use energy comes from electricity. And if we look out to 2030, we're probably talking about moving this up to 30% to be able to meet the decarbonization goals from this combination of clean power and electrification. And again, it's not just EVs, it's heating, it's industrial processing, it's hydrogen production. And what we always need to remember is all of these things are sharing the grid at the same time. So dealing with EVs in the grid and heating in the grid and industrial processing in the grid, each as sort of bilateral issues needing solutions, is just not going to work. We really need to think of the integration between all these end uses, many of which provide very large loads in relationship to some of the activities that we've been using the grid for today. The other thing is that, as we heard from that last outstanding talk, is that, energy assets like storage and electricity generation, PV panels are being a great example. They come in many sizes, and they're going to be widely distributed between the bulk power system, utility scale facilities, and the distribution system. Which is very different than the system that we had a decade ago, and we've just begun that transition of managing a system that includes generation all throughout the entire system. End user devices in the future will be able to smartly respond to supply side signals, providing demand response services. This is something, that what's amazing about our grid today is, whenever you want power, you can have it, and the grid was built to accommodate that. There'll also be two-way power flows. We'll have ubiquitous sensors. And I think also very importantly is our computational tools that we have to model, optimize, and control our energy system have vastly improved, and we can put those to work to help us deal with this more complex system. So next one. Thank you. Yeah, so the question is that, what is the cyber physical infrastructure needed for this 21st century net zero energy system? And how do we begin to accelerate the deployment of the devices and the cyber systems that we're going to need to manage this very complex energy system? So next, please. So what does the cyber physical system look like? Obviously, it's going to be pipelines and wires and all of those things, but we're going to be able to have a lot more device level control within the distribution system. And we'll have data that will, both at the utility scale and the neighborhood scale, allow us to do things like solar forecasting so the grid can anticipate and be ready for drops or large increases in generation. We're also going to be in much more closer to real-time optimization of this large portfolio of energy generating resources so that at all times supply and demand match, and that we're optimizing how and when and where we store energy to provide reliability and resilience. And finally, our grid will be rich with real-time analytics, both regarding to resilience measures, but also optimization of power flows and so forth. So this is the one aspect of this energy system of the future that we can create, that we need to begin to make more progress towards. Next one, please. Okay, so at the heart of this new 21st century energy system are three critical and interconnected challenges. I've been talking a lot about electrification. We're also going to be building a net zero power grid. And all of this needs to be done in the context of an evolving climate, which creates challenges from reliability and resistance point of view. For example, more extreme weather will drive much greater loads, for example, than we'd anticipated when we build the infrastructure. And climate-induced floods and wildfires will also impact our ability to manage the grid. And finally, at the end of the day, a net zero power grid, is going to be the key to electrification. And again, getting supply and demand to match is going to be crucial. So I'd like to focus on the electrification piece because it's expected to be responsible for a significant fraction of our emission reductions, particularly in this next 10 years. So next, please. Okay, so just sort of looking at some of the kind of loads that we're talking about. These are in quads. So we've got cars and light trucks, a really, really large source of energy. Now, of course, when we electrify that will be more efficient. So it won't be such a big load, but nevertheless, still very significant. We've got heat pumps. There's also opportunities in industrial processing with induction melting, infrared drying, batteries or battery hybrid systems with hydrogen for long haul trucking. And then there are other opportunities, but it's really these ones here at the top that we anticipate this is going to play such a big role in. So if we move to the next one. Okay, so what do we need? So to get to the target where we are at 30% of end use energy by the year 2030, we're going to increase the rate of electrification 4 times the historic pace in order to meet our climate goals. Okay, so basically every year we need another percentage point of our end use energy to come from electricity. And there are 3 components of this. One is the electric equipment innovation. That's both on the supply side and the generation and on the end use side. We also need to think about the electric grid infrastructure and operations innovation that again allows us to sustain the reliability and resilience that we need. And there's also going to need to be social and institutional innovation in terms of codes, and standards, and rate structures. We just heard an excellent discussion of net metering incentives and so forth. But at the end of the day, this is going to work. Electrification will work if people feel confident that it's going to be affordable and reliable, and they can count on it for all the energy they need. So next one, please. Yeah, and again, electrification, not only provides a critical element of decarbonization, but to the extent that electricity prices would be much less volatile. It reduces our dependence on volatile oil and gas prices, which of course is top of mind for everybody today. It also enhances equity immediately with better air quality, better comfort and resiliency for homeowners, and can reduce the cost of energy for transportation by about 50% on average for the US, particularly today with these very high prices. And also this provides us the opportunity with international leadership through innovation that could be shared elsewhere. So moving to the next one. Yeah, so this is just an example of the benefits of electrification. So this is Southern California, right where we're sitting. This is ozone. And 2011, 2030, and 2050, you see dramatic improvements in air quality associated with high electrification scenarios. This was some nice work done by EPRI. So moving to the next slide. Yeah, so there's huge benefits clearly, but there are also challenges. So this is a little schematic illustrating household instantaneous household power demand. So basically how much current that you need to draw from the grid. And if you add 2 EVs and you're charging 2 EVs, you're basically going to double household use. It differs in different parts of the country, but anywhere from 2 to 3 times the increase power demand by this whole suite of devices that again are all sharing the grid. So next one. Okay, so what happens when we have, if you just have 1 EV, in a neighborhood, or 2 or 3 or 10% or 20%, maybe it's not a big deal. But when everybody starts to do this, you're really going to need to take a hard look at the distribution system and look at to the extent that it's prepared for these increased loads. There are already places experiencing challenges and needing to do upgrades. And we don't want to do upgrades over and over and again. What we want to do is we want to figure out, okay, what is this end state going to look like, so we can make the climate smart investment in the infrastructure upgrades, so we can just do this once, so it's faster and much more efficient. So next one, please. Yeah, and this is just some data from California. This is illustrating the impact to the grid of electrification of transportation and heating. And the top row there shows basically the summertime electricity demand under high electrification scenario. The light blue is the EV loads, and the red is increased building loads. So in the summer, we're talking about peak loads increasing maybe 30, 40, maybe even 50%. If we look in the winter, what we see is that, again, we have sort of a much more heavy heating demands, particularly in the morning. And so if you compare the 2018 power demand during the winter with the case in 2045. This was for California. We're talking about doubling the power requirement, which is very significant and problematical in light of the fact that, for example, California, really has an excellent solar resource as its primary renewable. So all of these things are going to need to be coordinated and managed and anticipated so that we can be successful. And a key element of this is also, if we can smooth out these loads, that will put a lot less stress on the distribution systems and as well as the bulk power system. So moving to the next one. Yeah, so that was those were California-wide projections. So again, significantly more energy. So now we're talking about not only distribution level upgrades, but we're talking about large upgrades in the bulk power transmission system that will be needed to do this. So there's basically a cascade of effects rolling up from neighborhood level increases in power demand. Next one, please. Yeah, and so this is some really nice work from Southern California Edison, who's really been forward-looking in what will it take to convert the grid from sort of what we have today, which is characterized by sort of one-way power flow from the bulk system down into neighborhoods and customers in the distribution system, and in this future, this more digital, flexible, interactive grid that needs all of the cyber intelligence as well as physical infrastructure to make a system like this work. And again, Southern California Edison laid out a long-term plan of near-term, midterm, and even beyond, imagining what kind of infrastructure, grid controls, communication networks, sensors, and edge computing, and the physical assets in the grid, including very important technologies such as long duration storage. Moving to the next one.
Sally, we've just got a couple minutes left.
Okay, I'm going to wrap up. So the Biden-Harris administration is committed to make rapid and sustained progress on our 2030 and 2050 goals. It is incredibly exciting for me to be in the Eisenhower Executive Office building, where I work with so many fantastic colleagues in the Domestic Climate Policy Office, the OMB, the National Economic Council, National Security Council. People are really laser focused on these issues, and it's there is a tremendous amount of work being done every single day. You might have heard that last week the president announced he was going to use the Defense Production Act to secure supply chains for solar, heat pumps, and a long list of electrolyzers. And so forth. So very exciting, using every tool available. We have a long-range plan that lays out a blueprint for getting to net zero. And many of the technologies needed to do this are now cost-effective, but there's going to be more innovation needed. And as I pointed out here, we also really need to dig into now thinking about the cyber-physical system that's going to be needed to maintain the reliability and resilience of this increasingly complex energy system. And we really welcome your input and ideas. And, if you have specific thoughts, please reach out and get in touch with us in the Office of Science and Technology Policy. So thank you very much.
Thank you, Sally, for that great overview of everything happening in the DC circuit area. We're right up against time, so since you've moved yourself to DC, I can just ask you one quick question, which is, what are the chances for the climate portions of the Build Back Better plan going forward right now, and what happens if they don't move forward?
Right. Well, I do think that there is broad support as long as we have a very broad vision of what a climate portfolio should include. So I think very positive conversations.
Great. All right. Thank you so much for taking the time to go over all that with us. It was wonderful.